Okay, this is scenario 2 for hypothesis test where the population standard deviation is known. So the EPA reports that exhaust emissions for a certain car model has a normal distribution. It's good that they told us that so we can run the test with a mean of 101.45 grams of nitrous oxide per mile and a standard deviation of 0.4. The car manufacturer claims their new processes reduces the emissions. By the way, this is probably important. Reduces the mean level emission for this car model. A simple random sample of 28 cars is taken and the mean level of exhaust emitted for the sample is 1.27. All right, this right here is my X bar because it's the mean level for the sample. So what's the initial hypothesis? Well, the initial hypothesis is that an initial hypothesis is always the status quo. It's the general claim, which in this case is 1.45 grams. All right, so the initial claim is 1.45 grams, but the company is trying to say, hey, you know what? It's been reduced. So my alternative, fortunately, is just going to look exactly like the null. So it's 1.45 grams, but it says it's reducing. So we're going to say that this is less than 1.45 grams. So now the next step in our on our recipe card is to define our parameter. And so our parameter in this case is let mu equal the true population mean grams of nitrous oxide. Someone else may say mean grams of exhaust, but specifically it's the mean grams of oxide, and it's really specific to this car. The next thing are the conditions, which we're assuming them to be true. And they told us they were normal. They also said that it was a simple random sample, and we can assume that there's a lot more cars than 280 of these vehicles. So the next thing is write the equation. So our equation is Z equals X bar minus mu sigma divided by the square root of N. So that's our equation. And then we're supposed to draw a graph and shade. Well, that means I need to kind of identify some of what we're working with. So what we have right here is we have a mean of 1.45 because we always center it on the claim. So this is the mu. But then we ended up getting an X bar of 1.27. So this was my X bar, happens to be 1.27. And we said that it's going to be a less than. So we're shading off to negative infinity. All right. We don't have data to enter this time, so we need to come up with a list of our inputs. So our inputs are mu equals 1.45. The standard deviation in this case happens to be, and we have to look for it, standard deviation is right up here at 0.4. And that's the standard deviation of the population. And then we have an X bar equal to the 1.27. And we have an N of 28. So at that point, we're going to go ahead and plug into our equation. So this is going to be number 8. So plugging into our equation, it's going to be the probability that Z, and what did we have? We had a less than, and we're below 1.245, so it's a less than 1.27 minus 1.45 over 0.4 divided by the square root of 28. Now, some of you are going, hey, you didn't multiply by 2 this time. Only multiply by 2 if it's a not equal. And since this time we don't have a not equal situation, we don't have to put the times 2 in there. All right. So we're going to go on to step 9, and we're going to go ahead and do our calculations. So step number 9, stat, test, z-test, and my mean happens to be 1.45. My standard deviation is 0.4. My X bar is 1.27, and my sample size is 28, and we have a less than shaded. All right, so make sure you have a less than. All right. When I do that, I end up getting a z equal to negative 2.381 and a probability 0.0086. So the probability that z is less than negative 2.3811 equals 0.0086. This is number 9, and this is my p-value. All right, so real quickly, I'm going to do that one more time. Stat, test, z-test. My mean of 1.45, that's the population mean. The standard deviation of the population, 0.4. The sample mean is 1.27, 28. And we used a less than because that's what was given in our alternative, and we press calculate. Probability less than negative 2.3811 equals 0.0086. All right, so I went back and I'm looking, I'm going, okay, I'm looking for alpha to make my comparison, and I don't see alpha. Well, if I don't see alpha, we're just going to use 0.05. All right, and we'll do that every single time. So we have p-value alpha. Well, this is the 4 places, so I'm going to make this the 4 places. And real quickly, I can see that 500 is bigger than 86. So what do? If the p-value is less than alpha, the p-value is less than alpha, we reject the null. So our decision is number 10, reject the null. So now I need to be looking, and I go to number 11, and I'm going to write my conclusion. And I'm going to write my conclusion based on the rejection one, because we chose to reject. So our p-value is whatever we had. We reject the null. And let's go through that real quickly. So number 11, our p-value is 0.0086. Our decision, we reject the null. Apparently a kitty cat's not very happy. There is sufficient evidence at alpha. And by the way, they didn't give us alpha, so we used the 0.05 equal 0.05 to suggest that. Now we restate our definition of the parameter, which is that the true population mean grams of nitrous oxide is, and what was our alternative? Less than 1.45 grams. Is less than 1.45 grams. So in this case, we rejected this and said, you know what? We have evidence to suggest that they were successful in reducing it. So we rejected the null, and that means we believe this because that's our only other option. So it appears that the company was successful reducing the nitrous oxide emissions. Now, this is about 0.86%. What that means is there's about a 0.86% chance that we'd get a test statistic of 1.27 or smaller if in fact this is true. And it's like, you know what? We're unlucky, but we're not that unlucky. As a matter of fact, we set our unlucky standard at 5%. Okay. All right. We will do one more in the next one more scenario in the next video.